Okay, should I go?
I'll just maybe say
Okay.
a couple of things. So hello everyone to this edition of our virtual string seminars. And today we're delighted to have Sean with us. And he's going to talk to us about bootstrapping matrix quantum mechanics. Okay, over to you, Sean.
Yeah, well, thanks. Thanks for the invitation. Thanks everyone for coming. You know, please ask plenty of questions as I go along. That'll be great. So I'm going to talk about this paper with these two people. Shisha is my student at Stanford, and Yorit is a postdoc at Stanford, and it just appeared on the archive a couple of months ago. All right, so let me just say a few words about motivation. This somewhat big picture motivation. It's not going to connect very directly to what I say in the talk. It's mainly about why we might want to care about matrix quantum mechanics. So I think it's obvious at this point that space is emergent. It's not a fundamental concept. And in particular, through ADS-CFT, we understand that quantum mechanical theories of large N matrices can produce a semi-classical gravitating spacetime. But I think it's also fair to say that in general, we don't really understand how the matrix degrees of freedom manage to rearrange themselves into this space-time that's not there to begin with. And I think the matrix quantum mechanics is the purest manifestation of that, because if there's no space to begin with, right? So n equals 4 super Yang Mills on a sphere is a large N quantum mechanical system that does have emergent space, but you get some of the dimensions for free, right? You get the dimensions on the sphere are already there, and then the radial direction and the S5 has to emerge. But in matrix quantum mechanics, all the space emerges. So you're not gonna cheat, right? You can't, you can't try to build with the space that you already have, because there is no space to begin with. Okay, so I think to really understand emergent space-time properly, meaning space that really comes from no space, we need to know how to solve matrix quantum mechanics theories. Right. So the simplest theory, there are many flavors of matrix quantum mechanics. The simplest one, I guess, is of a single matrix, a single n by n large N matrix. And this can be solved exactly by mapping, by diagonalizing the single matrix and mapping the eigenvalues to free fermions. And this was a key part of the excitement in two-dimensional string theory in the early 90s that Schmidt and others did important work on. On the other end of the spectrum, the richest maximally supersymmetric, maximally everything theories are the Bfss theory and the BMN theory. And these have many bosonic matrices and many fermionic matrices. And I guess these are the ones one would really like to solve. They look a bit difficult at the moment, but that's, I guess, where we'd like to be heading. Fortunately, there are many theories in between having one matrix and many matrices. There are many theories in between, and these have varying number of matrices and also varying degrees of supersymmetry. And the current state of affairs is that pretty much any theory with more than one matrix is not solved. And I'm not talking about matrix integrals. I'm talking about matrix quantum mechanics, right? These are not just integrals over matrices. They're a path integral over matrices that depend on time. And so the current status, to my understanding, is that anything that we can understand better involving more than one matrix rigorously is a step in the right direction. Okay, so today I want to tell you some things, new things about matrix quantum mechanics with more than one matrix. Okay. And obviously the main difficulty is that once there's more than one matrix, you can't diagonalize them both at the same time. And so life is harder. Oops. Okay, so that's the big picture. And so now what I'm going to tell you about was directly inspired by a paper from a few months ago by Henry Lin, who is I believe, a graduate student at Princeton. And he did what I'm going to show you, but for the case of matrix integrals. Okay, so no time, just doing an integral over large N matrices. And actually, we subsequently learned that there's some similar ideas in the older paper, also with no time, integrals over matrices by Anderson and Kruczynski from a few years ago. So what that paper did is solve large N matrix integrals using positivity constraints. And as we'll see in a minute, and we're going to use the same philosophy for large N matrix quantum mechanics. It's a slight, what we're going to do will have some things in common with what Henry did, and some things will be a little bit different. With large N matrices, the main object is the partition function. And in quantum mechanics, the main object, at least from my point of view, is the wave function. Okay, so the strategy is going to be the following. We're going to want to calculate expectation values of simple operators like the energy or x squared or the commutator of x and y, expectation values of these operators in, let's say, the ground states. And the way we're going to do that is we're going to take these simple expectation values. We're going to use symmetries of the theory to relate simple expectation values to complicated expectation values. Then we're going to impose certain positivity constraints on the complicated expectation values, and these will seem to sort of feed back into quite strong constraints on the simple ones. As we'll see, I'm about to tell you, but that's the idea. And doing this, we'll obtain some, I think, new results for two matrix quantum mechanics. Okay, so one step away from one matrix. All right, so here's the plan for the talk. So I'm going to start with a very simple, which is a textbook and harmonic oscillator. Then we'll take a jump to one matrix quantum mechanics to get a feel for how the technology works. And then in the end, I'll talk about two matrix quantum mechanics. But by the time we get there, we'll already have everything in place. And so it'll be quite simple. Okay, so let's start with the harmonic oscillator. So here's the Hamiltonian. Let's see if this is working. There we go, that's the Hamiltonian. And so, right, and say let's say we want to calculate the spectrum of this Hamiltonian. So you can do it, of course, by numerically solving the Schrödinger equation. It's pretty simple, but here's how we're going to do it. So, so first we're going to use this identity, which we can think of as a symmetry, right? It's the time translation variance of the Hamiltonian. And so the expectation value in any energy eigenstate of H commutator O is 0, right? Because that's HO minus OH on the state. The H can act to the left, it can act to the right, and you get E both times, and they cancel, and so you get 0, okay? So this is true for any operator. Now we're going to choose two operators, x to the s and x to the t times p, all right? So we do the following. If we take these two operators and plug them into this equation, do some very simple manipulations with commuting stuff that we all learn how to do as undergrad, and you're going to get some terms involving, you can get rid of the p's, you get some terms involving, so you get two sets of equations. You use one of them to eliminate all the operators that are linear in p. There's some operators that go like p squared, and to get rid of those, you use the Hamiltonian. And that gives you this factor of the energy, okay? So if you plug these two operators into this constraint, what you get, and you do very simple manipulations, you get this recursion relation between expectation values of the operators, right? So here's x to the t minus 1, x to the t minus 3, x to the t plus 1, x to the t plus 3, and it also depends on the energy. And so what if it turns out, if you stare at this for a little bit, this means that once you know the energy, and if you know, x squared, then you can get all the higher x to the 2t's, all right? And by symmetry, the odd ones are all 0. X to the 2n plus 1, expectation value is 0, so that's a 1. All right, so okay, everyone happy with that? All right, so an harmonic oscillator, if you know the energy of an eigenstate and you know the expectation value of x squared in that eigenstate, then you know all the other expectation values from this recurrence relation that just follows from time translation invariance, okay, which is this symmetry here. All right, so now the name of the game is going to be the following. The bootstrap is that we guess E and we guess x squared. We calculate a whole bunch of higher x to the 2n's. Then we impose some constraints on these higher x to the 2n's. So let me tell you what the constraints are. So it goes like this. So clearly, any operator, if you square it, the expectation value should be positive. Okay. So for example, the expectation value of x to the 4th is positive. all right? But we can do a bit better than that by taking an operator that's a general linear combination of x's, right? So a simple case could be, let's say the operator could be C1 plus C2x, okay? And this thing has to be positive for all C1 and C2, okay? In particular, C1 and C2 could have minus signs between them, right? So this is a stronger constraint than just requiring like x squared is positive. So so this is a matrix, right? So now we have, right, so this becomes something like C1, C2x, C1, sorry, I'm doing it backwards probably, aren't I? C1, C2x. So you're going to get a matrix, which is something like, okay, basically this matrix 1x squared ends up having to be a positive matrix. Okay, so if I take, yeah, is that clear? Because if I take this operator, C1 plus C2x, I plug it into here, and I require this to be positive for all C1 and C2, that requires this matrix here to be positive, to have positive eigenvalues. All right, so if I truncate the sum at k, okay, where k is 1 here, then the k plus 1 times k plus 1 matrix, so this is a 2 by 2 in this case, has to be positive. So in general, this is the matrix, right? So this matrix is that. This matrix has to be positive. You could truncate it at any x you want, and it has to be positive or 0. And so the strategy that, sorry, I feel that maybe wasn't as clear as it should have been, right? So clearly, let me say that one more time. The square of any operator has to be positive. You could take this operator, which is any linear combination of powers of x, and for those to always be positive, it means that this matrix has to be positive, and this matrix is just this guy, right? 1x squared expanded, right? So 1x squared, x squared, x cubed, right? Is this matrices like this, okay? And these have to be positive. So that's a lot of constraints. As k gets bigger, that's a lot of constraints. And so the bootstrap philosophy, following, this is what Henry Lin did, is you scan over E and x squared, you impose this, you calculate this matrix, you calculate this lowest eigenvalue, and if the lowest eigenvalue is negative, you can exclude those values of E and x squared. All right, so here are the sort of plots you get. So this is x squared, this is E, x squared and E. These are different values of k, right? So you're increasing the constraint to impose. Look at these axes. These are very small numbers, okay? This is from 0.300, 0.305. I think these small, we're quite zoomed in already, is what I'm trying to say. The red cross is the analytic result, okay, of the ground state of the harmonic oscillator. This is the energy, and this is the expectation value of x squared. And by the time you get to k equals 9, you know, you're pretty zoomed in, okay? This is the same thing, but this is now the first excited state. So what you actually find is a plot like this, x squared E, and then there are a bunch of islands, which are the eigenstates, okay? And so this you can do extremely quickly on a laptop, okay? This is not complicated numerics, and it's okay. So you find the spectrum that you already knew. Of course, the higher up you want to go in the spectrum, the bigger k has to be. Right. So this is the philosophy. Let's see. Any questions?
Sean.
Okay.
Sean. Excuse me. May I ask a question? I just want to understand. E was an expectation value of energy, right? So we can we can ask the question: what is the expectation value of x squared in any eigenstate?
That's correct.
So it means that E should be almost a continuous spectrum from some ground state to infinity. And in your picture, E is a particular number.
You get these islands. Oh, sorry. Yes, I think I put G equals 1 here, of course. Yes, sorry, I should have said this is with, then we put G, the coupling equal to 1, but of course it doesn't matter. So yeah, so it's not a continuum is going to come in a minute, but in this model, it's discrete. And so you get a bunch of islands. So indeed, there are different energies that are allowed. And for each energy, you have the corresponding x squared.
May I also ask a question?
Did I answer the first question? Was it done? Or?
Sorry.
So just to clarify, in principle, if I want to have the full story, I can have almost continuous line of this red islands.
Why do you say almost continuous?
Because the energy spectrum is I don't know, it's not continuous, right? It's discrete.
Yeah.
So in principle, I will have red islands for each value of E, and and it will be like almost a continuous line on the x squared E plot.
Yeah, it looks like this. In fact, you can solve the classical harmonic oscillator, right? And then there's some line that gives you E and x squared, and it looks something like this, right? So it's roughly these dots sort of roughly follow the classical line. Yeah.
Thank you.
So please go. Next question.
Do you have an idea why this procedure converges at all? After all, you could imagine that you impose more and more inequalities, and you still are left with an island which doesn't diminish. If you don't have a theorem, at least an idea why.
Yeah, no, I think for this case, actually, it is almost a theorem. Actually, yeah, we put a comment in actually the version that's not on the archive yet. Yes, I think there is a quasi-theorem, actually, more or less a theorem, in that this does converge. In fact, it does converge, yeah, in this case. For
any G, for any G, for any coupling?
No, that's very good. Yeah.
Same question, by the way, in one matrix model.
No, very good. Yeah. So we still haven't explored things like, for example, if G is negative, right? Something bad probably should happen. That's right.
Okay, it would be interesting to see the arguments.
Yes, I can. Yes, I don't know if I can reproduce it right now, but we do have an argument, and yes, yeah. I don't know about the later cases, but this case, I think it converges.
And for the one matrix model as well, you have some arguments.
Yeah, well, so for the one matrix model, there was actually an argument. Let me come back to that one in a minute.
Okay.
Sorry, I just wanted to clarify. I think, it's along the line of the last question that was being discussed. So, can you just say, about the convergence properties? So, how much does it depend on this value of G? For instance, if we take G very close to 0, or rather, just consider the simple harmonic oscillator, would it converge, as well as it does here?
That's an excellent question, and really we haven't had time. There's lots of exploration that has not been done yet. I don't know. Yeah,
okay.
Let's see. You can't just scale G out of. Let's see. Is G? I mean, probably you can.
No, I was just saying that you don't have this enharmonic term at all. You just have the harmonic oscillator.
No. Yes,
would the procedure would be as good, or?
I don't know. And actually, there are other. Yeah, I don't know. And also, I don't know. For example, if there was a double well potential.
Exactly. That was my second thing. So if there are two two minimas, would it capture both the states in excited states in both the minimas equally well? It's not. Yeah, you're saying it's not clear.
This is a great. We haven't explored a lot of things yet. Yeah.
All right. Thanks a lot. Thank you.
Sean?
Yes. Anyone else?
You made a comment that in order to go to higher eigenvalues, you would need to go high up in the K, the number of size of the matrix that you consider. Why is that? Why is it that you have to consider bigger and bigger matrix?
Okay, that's just an empirical fact, but also intuitively. I mean, there's more and more information, right? It seems natural that you need more constraints. If you get the whole spectrum.
If you were to do this, let's say with a fixed K, then you would get a bigger and bigger island as you go up?
I believe that's what happens, yes.
I see, okay, thank you.
Like you can already see that a little bit in these plots, right? So, well, the axis is the same. Well, okay. Yes.
So just one quick question.
Yeah, go.
Is it true that I can rescale time and X to bring the coupling completely out?
Yeah, that's what I was just wondering. No, probably not, right? Because probably something like the mass over the coupling is probably right. We've already set the mass to 1, and that probably
okay.
That probably ate up the freedom there, right? Because there's a dimensionless coupling.
Right.
Good. So that was yeah. Go. I should say we've
I had a question.
Yeah, go.
Sir, if we are increasing the energy, why the width of the graph is reducing?
So are you
in the second graph, it's
are you asking why does it have this shape?
It's meaning why it's getting narrower with energy.
I'm sorry, I can't quite hear the question. Could you say it again?
So why is it getting narrower with energy? For smaller energy, the width of the graph is larger, while for the other case, the width is much smaller.
So are you asking about the shape of the region?
Yeah.
So actually, I think I don't totally understand that, but it may be related. I'm not sure. That if you look at the classical spectrum relation of x squared and e, it does something like this, and it may be that this shape is sort of going along like that. So this is kind of like classical physics already localizes you on this region, and the sort of the quantization is more about how it's localized along this curve, and that may be why you get some convergence in this direction faster, but I don't know. That's just a speculation. I'm saying that this elongation of the curve in the first excited state is roughly what the classical curve would be doing. But I have no deep understanding of the shape of these curves. Yeah, that's the short answer.
Thank
you. Good. I should say that we've subsequently found out that actually, I mean, people have been using these kind of techniques actually in quantum chemistry and things where there are complicated quantum mechanical problems. That using positivity is a thing that is done. Okay, so now let's do one matrix.
Just another.
Yeah, go.
So the positivity constraint, does it come, meaning for the case of energy, we can understand where positivity comes from. Is there, I don't know why it's true in general that the expectation value of any, okay, I got it. I'm very sorry.
It's okay? All right.
Okay. Yeah, thank you.
So now let's do one matrix. Okay, so again, we know this is solvable. So we know the answer. Okay, so we're just trying to build confidence in what we're doing. So for concreteness, we're going to take this Hamiltonian, this one matrix, quantum mechanics, right? So X is an n by n matrix, Hermitian matrix. P is the conjugate momentum, and we set the mass to 1, and so there's a coupling G. Okay, so now, So it's the same. The philosophy is the same. It's just a little bit more complicated. So first we have this. So first we want to relate expectation value. So first we use this one, which is you can think of as time translation invariance. And so, for example, if just an example of something you get, if you take O to be trace of X times P, you commute that with H, you get this relationship between trace of P squared, trace X squared, and trace X to the 4th. Okay, and this is just a virial theorem, in fact. Okay, so that's, you get relationships between expectation values by putting an operator into this equation. Now in this case, we want to impose a second identity, which is that we're going to have gauged, we're going to be interested in gauged matrix quantum mechanics. So they have a singlet constraint. Okay, and so that means that physical states should be annihilated by the generator of the SUN symmetry. So the generator can be written like this. It's commutative of X and P. This is just the identity, and this exists to make trace of G 0. Okay, because there's some ordering, there's some questions about how you order the X and P's. So don't worry about that. So this is the generator of SUN, and then the trace of the generator against any operator should be 0. You don't even need this trace, but we'll put this trace in. That's just because G should annihilate the physical states, right? Okay, so we want this theory has an SUN gauge symmetry, and so all physical states should be annihilated by the generators of this symmetry. So for example, the simplest case of this is to take O to be the identity, trace of G is 0. So that gives you one relationship. If you combine that with this previous relation, but with X squared, then, for example, you find that trace xp is minus trace px is some number. Okay, so this is example of how you get expectation values using these constraints. Okay, so it's similar to before, but now with a gauged constraint. And now we do the second bit. Okay, so last time for the anharmonic oscillator, we got a closed form recursion relation for all expectation values. The key to doing that was that we got rid of p squared. Wherever p squared appeared, we could use the Hamiltonian to express it in terms of the energy. That's not going to work here because things don't commute, right? Because so trace, you'd have like trace px, or you could have trace p squared x squared, right? The p can appear in many places, and you can't get rid of all of them using the Hamiltonian only has trace p squared in it. Okay, so we can't eliminate p in a simple way. So we have to keep x and p, and we're not going to get a closed form recursion relation. All right. So the philosophy is you just take a selection of operators and write down a matrix that must be non-negative. So, for example, take the operators I, x squared, x, and p. Okay, and then build this matrix of expectation values. Right, so this is, right, you just take this matrix, take the matrix here, right? So this matrix is trace AI, AJ, right? That's what this matrix is, where A is I, x squared, x, and p, okay? And so you get this matrix, these ones vanish by symmetries, and so this matrix has to be positive, okay? By basically the same, so A dagger, their Hermitian, of course. So you build, right, sorry, exactly. So consider, how should I do this? Sorry. Write that better. You consider the string, the general operator, to be C1 times identity plus C2 times x squared plus C3 times x plus C4 times p. Okay, where C1, C2, C3, and 4 are just numbers. Then O dagger O should be positive. Okay. This positivity constraint requires that this matrix of expectation values be positive. Okay, it's very analogous to what we had before, except now we have x's and p's and traces. Is that okay? Does that make sense? So it's really the same as before, right? I construct a general operator. I pick some subset of operators. I build with some coefficients, some superposition of them, and I require a trace of O dagger O to be positive, and that imposes that some matrix of expectation values should be positive.
Sorry, just one small clarification. I mean, when you say the operators, when you list in the, do you say that, these operators are the trace x square, or, it's like that, or, so I'm just confused about when you say that, O dagger O, so is it something like trace x square, or it's like...
the trace comes after you multiply them. So yeah, I'm sorry, let me say this clearly. So you take the operator, which is C1 identity x squared x p. So O is still a matrix operator, okay? Then I construct O dagger O, matrix multiplication, okay? Then I take the trace of this. Okay. This guy has to be positive.
I see. All right, thanks a lot. Yeah.
Oh, thanks for asking. Yeah, that's good. So now we have a big thing that has to be positive, but then from before we have some relationships between the operators, right? So for example, we go back, and here we have trace p squared in terms of operators, and we know trace xp. So in this big matrix, we know p squared and we know trace xp, okay? And so positivity of this matrix becomes this constraint. Well, actually this is one constraint, which involves x squared and x to the fourth. And there'll be several such constraints, right? So the idea is you take a whole bunch of operators, you consider all possible strings. Basically, you consider strings of x's and p's. You build this matrix. You eliminate as many expectation values as you can using these constraints, and then you bootstrap. Okay, so let me say that one more time. So you take all strings of x's and p's that are of length less than L, right? So that could be, let's say if L is 4, that could be like xp, px, for example, right? That would be one such string. So clearly there are of order 2 to the L such strings, right? You get to choose X and P every time. Then you build a matrix by, you multiply pairs of these strings. So maybe it's this one times, I don't know, P to the 4th. You take trace expectation value and you get a matrix with order 2 to the 2L entries, right? So just like this matrix, just bigger, right? Then, right, so then you have a whole bunch of positivity constraints. Then you write down all relationships of the types we just discussed between these strings. And furthermore, now this is the only point where we're actually going to use large N, but it turns out it is important. We're going to impose large N cyclicity. So that relates trace xp cubed is equal to trace p cubed x. So classically, these would just be equal, but they're also quantum commutators. As you impose the cyclicity of the trace, you get quantum commutators. And these can involve terms that, and at large N, these would generate multi-trace terms, and at large N, you can factorize those, okay? So at N equals infinity, there are relationships like this one between the expectation values, okay?
I'm sorry. In the large N limit, is it like all the long trace operators can be factorized into free field operators?
No, it's not. No, it's so we're gonna. Sorry, I might have not heard you, but at so these are all going to be relatively short. Like the length of these operators is not going to be, N is going to be strictly infinity, and so then any product of traces can be factorized. So I'm just using here the trace of O tilde expectation value is equal to, I can just break it up into 2 expectation values like that. That's all I'm using. Is that the question?
So I just wanted to ask that in the large N limit, can we factorize all product of operators into something like a product of free field operators with interaction terms suppressed by 1 over N?
So again, I'm not entirely sure I heard, but yes, a large N. Okay. At N equals infinity,
I'm sorry.
Any product of traces can be factorized. Yeah.
Okay.
So that, by the way, a nice thing here is quite complementary to other numerical approaches such as Monte Carlo, where you have to take N equals 10, 20, 30. And actually here we're starting at N equals infinity.
Okay, so that was actually my question. So, but it seems from your formulas that N appears in your expressions. So, I mean, when you do the numerical...
Yeah, once you scale everything, N will drop out. There won't be any N's left.
Okay, that's excellent. Okay, and one more quick question about, so it seems that, so, when you have the matrix and you're trying to, you will say that the eigenvalues of the matrix are all positive definite. That's what you mean, right? When, so even in the matrix method, in this matrix case, quantum mechanics, then you written this matrix in your previous slide, right? And then you're going to take that matrix and you're going to write down all the eigenvalues of that matrix and then say that this is positive. That's your constraint, right? Do I understand that right?
Before it's a matrix with X's and P's in it, right?
Right. So when I say the matrix, the one that you wrote in the previous slide. So in the previous slide, you had this, so you're going to take this matrix and you're going to say that what are the eigenvalues of the matrix, and you're going to put positivity constraints. That's that. Okay, so in this case, you are assuming that individual entries into this matrix is your data. Is that right? Like, they are free data. Is that?
Exactly. So let me just repeat it exactly. So imagine, take all operators up to length that are these products of 2 strings, right? So let's say L is 4. Okay. So then you take all traces of up to 8 X's and P's.
Right.
You develop this matrix, and then you have 2 to the 8 variables. Okay.
Right.
There's a whole bunch of constraints on those inequalities, and there's also a whole bunch of equalities from this guy, right? So these terms give you some linear equalities on the variables.
Okay.
These guys give you nonlinear inequalities, and this trace condition gives you a quadratic equality.
Okay.
And then what you want to do, if you want to find the ground state, we're going to come to, is you're going to minimize on this space that has So it has a bunch, it's like a constrained minimization problem, basically, right? You have a whole lot of many variables, a bunch of equalities, several inequalities, and then you try to minimize subject to that.
So my question would be, how important are those equalities? Can't we just get rid of the equalities altogether and just minimize on the whole matrix?
Yes, I think that's actually so yes, you can, sorry. So this is a question of just mathematical efficiency, right? So I think yes, it turns out to be efficient to solve the linear constraints and then minimize on this reduced space.
It's always important to take care of these constraints. I mean, is that right? Otherwise, we'll never get a, let's say we increase the number of...
Crucial. Yes, it's crucial. I don't have the...
I mean the constraints, I mean the equality constraints, are the necessary, like the cyclicity constraint, are the necessary...
Yes, they are. Okay, so again, we haven't... There's even less of a theorem here there was in the previous case. So I don't know exactly what is...
Presumably you are looking at, this matrix of a given size, and the more you increase the size, you get better values, right? So let's say, you get better values for, the matrix size of, let's say 2 cross 2, and you increase it to 10 cross 10, maybe, it converges. I mean, is that a possibility without the equations, I mean?
No, I think you need, so actually, I think, for example, the cyclicity thing, it's funny. I don't fully understand this. It would be great if we could understand it better. So, for example, the cyclicity constraints, which are quadratic, are a small number of the total number of constraints, but I think they're probably quite important.
I see.
But I don't have a theorem. Because if you remove them, very good. So at infinite n, the spectrum is continuous. And at finite n, it isn't.
Well, the spectrum is continuous, but you are looking at the ground state energy, right? So you are basically minimizing on a large set of on a large data set anyway, right? So I'm just asking that you're somehow reducing the data set by using these equations. So I'm just asking that how important is the reduction?
No, I think it's quite important. I don't know. I suspect that some equalities are more important than other ones, and I don't know. Our strategy at the moment, because especially you're going to see that when we get to 2 matrices, we're really fighting against numerical time constraints, right? Computational constraints. And so the more constraints, the better, right? I mean, you want to reduce the variables as much as possible.
Yeah, that's
so our thoughts were more in these practical lines and less about what's the minimum set of constraints that in principle would give you convergence. I don't know the answer to that.
Thanks a lot.
Sean?
Yes.
So instead of looking at singlet states, I could have said that let me look at states in some representation of UN that would also give some condition, and you can use the similar methods for non-singlet states.
Wonderful. Yes, fantastic. Yes, of course. Yeah, right. Good. Fantastic. Yes. Yes, is the short answer. I'm pretty sure we haven't thought about it. Yeah. Yes. I think there's a lot of things that one could do. I'm going to show you a plot in a couple of slides with some thermal stuff, but that's not quite the same. Yeah. So yes, I totally yes. You definitely could, right? You could. Let's see. So basically, you'd have to this constraint would change to something else, I guess, right? But you could definitely do that.
Right.
Now, I don't know how, well, 2 matrices, if you like, includes non-singlet things from the 1 matrix point of view, right? If you like, so yes, you can definitely, in principle, do that.
Thanks.
So at infinite n, so the spectrum is continuous now. And so the name of the game is, as I was just saying, so you've got lots of variables, which are all these expectation values. You've got a whole bunch of constraints, equalities and inequalities between them. And now what we do is we try to minimize the energy. We do gradient descent on this space, basically. We minimize the energy subject to the constraints. And that's just a numerical thing you can do. But you don't have to. You can just fix the energy. You don't need to minimize it. But we'll see that the constraints work better the lower the energy is. Right. So in a way, you can just fix the energy. That'll give you a slice, and that's another constraint, right? And yeah, that's fine too. All right, so let me show you what I mean. Let's see. Yeah, let me show you some pictures. So this is for one matrix. So this is the energy. This is x squared against g. We've set the mass to 1. And so this is L that I was telling you about. So these are solvable. So the solid line is the exact n equals infinity solution from fermions or collective fields or whatever you want. And basically, by the time L is 3, it's already on, by I indistinguishable. Okay, so L equals 2. It's not, but L equals 3 is already on the line. So again, I have no proofs of convergence, but this thing seems to work. So let me come back to, there was a question about convergence. So what this suggests, that actually this argument I'm about to give you is in Henry Lin's paper, that, let me get this right, that actually the ground state is essentially saturating these constraints. Right, because, let's see, I should have thought about this beforehand. Sorry, before I do that, let me just show you. So let me finish showing you the plots. So the energy and x squared basically converge by L equals 3. And here's a plot, here's just to give you a sense of how the energy works. So this is energy, and this is trace x squared, okay? So what I'm showing you before here, this was the ground state, right? So the ground state, our approximation, the ground state energy is what we get by minimized. So this is the allowed region, which is L equals 3. This is the allowed region, right? And so what we've done to make these plots is to minimize the energy on the allowed region, which is here. And then you can get the value of energy, and you get the value of x squared, which are these 2 points. However, if you don't have to, you can also just fix the energy to be whatever you want. For example, here, okay? That's an allowed excited state, okay? And so then this is the range. So what the bootstrap gives you here is a range of expectation values of x squared in that state, right? So as you see, the higher in energy you go, the weaker the constraints are. And just to check that this is sensible, this is the thermal. By thermal, I just mean within the singlet sector. This is the thermal state. And so the thermal state is a finite energy state that has a value of E and x squared. And it's allowed. It's compatible with this bootstrap. I should say everything I just said here, it doesn't need to be an energy eigenstate. It can be any Gibbs state, right? So any density matrix rho that commutes to the Hamiltonian, you can calculate expectation values in that state. And this method will work.
Just a small question. L here is the number of components in the matrix.
L, it's the size of the matrix. So the number of components is 2L roughly.
Thank you.
Right. So the idea of convergence is somehow that right. So in this single matrix, what you're really solving for, there's some eigenvalue distribution, right? As a function of x.
Sean?
Yes, sorry, yes.
Sorry, in the case of one matrix model, is the analytic answer known at large n?
Yes, that is the analytic answer is a solid line in these plots.
Oh, okay.
Okay. Yeah. So we're on the nose of the analytic answer already for quite a small value of L. So yeah, okay. So let me not say anything about convergence, just that, it looks like it converges, at least. So indeed, I don't know what would happen with the, I know people care about upside down harmonic oscillators and things like that. I don't know. All right, so now let me see. So now the whole point of this whole exercise was try to go beyond the known into the unknown. And so we're going to look at, this is the simplest two matrix quantum mechanics. I guess originally studied in the 80s by Hopper and others. So let's see. So basically the strategy is the same as before. except now for one matrix, except now we have to write down strings that have x, y, px, and py in them, okay? So if we restrict the strings to have a certain length, there are now 4 to the 2L entries of the matrix, right? Because each entry of the string can be one of 4 things, x, y, px, or py, right? So so the matrix gets bigger exponentially quicker with L, right? So if we constrict, if we take L to be 3, okay, there are now you know, a lot of entries. Let's see, what is that? 2 to the 4 times 3, right? So we easily get to, you know, these are big matrices, okay? And so to help us a little bit, it's not strictly necessary, but we impose an extra symmetry to get rid of some more variables. We impose rotational invariance. And so there's rotational here means O2. All right, so there's just X rotations in X and Y. That's the symmetry of this Hamiltonian. This is the generator, and you can restrict to eigenstates of angular momentum. Now, okay, so just before I show you the results, so as far as I know, this 2-matrix quantum mechanics is not solvable, all right? So we'd like to have a sense of how well we're doing. And so we did something that I think is a little bit nice, so I just wanted to quickly tell you about that. So we're going to check the results with a Born-Oppenheimer wave function. So this, what I'm telling you now, is not the bootstrap, right? It's what we're going to use to benchmark the results. And so we're going to just make up a wave function, okay? So the wave function is the following. You have x and y, you diagonalize x, okay? If you diagonalize x, then the y Hamiltonian becomes a bunch of harmonic oscillators, right? Maybe this is familiar. So if you take this coupling, if you diagonalize x, this becomes a bunch of terms like xi minus xj squared, yij squared, right? They're a bunch of Hamiltonians for y whose energy depends on x. So the Born-Oppenheimer ansatz is that you take all of the oscillators of the y for a given x and you put them in their ground states, okay? So that's this, right? This is a Gaussian for all the y, the entries of the y matrix, whose frequency depends on the separation of the x's. And then we allow ourselves a function of x. So that this kind of class of matrices are now just solvable. We can minimize the energy within this class of matrices because we reduced it to a single eigenvalue problem, and single eigenvalues, single matrix problems are solvable. What's quite nice that I had forgotten until recently, so let me just remind you. Actually, Born-Oppenheimer wave functions give you both upper and lower bounds, actually. So as a variational wave function, it gives you an upper bound, of course, on the ground state energy. That's rigorous. But actually, it also gives you a lower bound. And this is something you may remember. So if you just write down the effective Hamiltonian, which is something like, you know, the kinetic term for the x's, plus the sort of effective potential from the w's, right? The ground state energy of all of these guys. This Hamiltonian actually gives you a lower bound on the ground state energy. So you get both from these Born-Oppenheimer wave functions. That's a general thing. Okay, and so we did that, and then so here are the answers. So again, we're limited by computational resources, if you like. So we have L equals 3 and L equals 4. Okay, this is how many how many things what we're doing. And so, and these two gray dashed lines are the rigorous upper and lower bounds. Okay, so this is the L equals 3, and this is L equals 4, and it's within these two bounds. And so, right, so one if you like problem with this method is that we don't know in advance how close we are to convergence, right? I mean, if this happens, if you get to a point where things are on top of each other, then you know you've converged. But until that happens, you don't know that you've converged, right? And so at the moment, we don't have L equals 5. And so I don't know for sure how close these orange dots are to the actual answer, but I know they're not too far away because they're within this gray region, okay? And so we also have the expectation values with trace x squared and also for the commutator, okay? And as I should say, we did one other, yeah.
I'm sorry, I'm interrupting in the middle again. I just wanted to know if there is some, sir, am I audible clearly?
I'm sorry, could you say it again?
Audible. Sir, am I audible?
So I think you cut out, and I just didn't hear the first half.
No. Sir, am I audible, sir? I'm very sorry I'm taking your time. Sir, am I audible? I just had a small question. I just wanted to know for some motivation for how we are choosing L, meaning is there some underlying quantum theory through which we are defining what the L's are, or we are plotting it numerically to get some convergent solution?
I mean, so we want to take L as big as possible, right? So L, the upper bound on L is set by how powerful a computer is. Right, so here, and most of the previous stuff was on a laptop, but it's not trivial computationally. So, so let me just also about convergence. So another thing actually we did is that there are some Monte Carlo results for this model, the same model as a function of temperature. And you can take the zero. I mean, what's nice about this method is it's quantum, right? So we're at zero temperature, but you can take the zero temperature limit of the quantum Monte Carlo results, and they've been done for the massless theory, which is sort of the limit of this curve. So this is actually G over M in some power. We set M to 1. So the massless limit is sort of over here. And actually we extrapolated and we agreed to like 2 decimal places with the Monte Carlo results in the massless limit. So actually I suspect that these orange lines are quite close to convergence, but we don't know that yet. So let me just quickly, yeah, maybe we can come back to the questions in a minute. I'll just wrap up and then be happy to take more questions. So what the main point I've been trying to say is I think positivity constraints give, I think, a powerful approach to matrix quantum mechanics wave functions. We have new results for 2 matrix quantum mechanics. I think that more matrices and fermions are definitely doable in principle, especially with rotational invariance, which can really restrict the number of operators you have to worry about. Also supersymmetry, of course, is, it goes both ways. You have to worry about the fermions because there are more matrices, but there are also stronger constraints, right, due to supersymmetry. And so something we are slowly starting to think about is how powerful supersymmetry is in this context. And I definitely think that characterizing the Bfss ground state is by no means out of the question. I think it's in principle accessible to these methods. Non-zero temperatures are also possible. I told you we matched some Monte Carlo results. Maybe we can try to learn something about black hole microstates. And of course, what would really be great, of course, expectation values are very simple, but what you'd really like to know about the quantum states are also more complicated things, like what is the entanglement in the quantum states. And it would be nice. I don't know if those could be accessible with these methods, but I hope that they can. And I really should emphasize, I really think that eventually, if we're going to understand holography, we have to know how to understand matrix quantum mechanics, right? It's just, it has to be done. Yeah, I hope to continue trying. All right, thanks.
All right, thanks, Sean, for that really wonderful talk. So maybe all of us can unmute ourselves and clap for Sean. So now we can have more questions. There's one question in the chat.
Okay, let me see that.
I can read it out if you want.
No, I got it.
Okay.
Yeah. So actually, very good. So the question is, did you try to compute the energy of the one matrix case for non-singlet states? So actually, I think Shumit asked the same question. Yes, I think no, we haven't tried, and I think it's definitely should definitely be doable, and it should be simpler than the 2 matrix case. It has a similar flavor. So the answer is no, we have not done it. And I think, I mean, you know, our objective was to get beyond one matrix, but I think there are definitely interesting questions with one matrix that could be studied, including the non-singlet sector. Yes.
Can I ask a question about the linear constraints you're using? So you had this HO expectation value, and in case of these one matrix series, you also had the GO. But do you know if in principle you could get more linear constraints, or do you know if this is the
very good. I don't think so. So, I mean, let's see. These are the ones you have a right to based on symmetries.
Mm-hmm.
Let me. Yeah, I mean, I don't know if you could try doing things like squaring. Yeah. No, I don't think there are other ones. Yeah.
Okay. And do you know like which choices of O are enough? Like in the anharmonic oscillator, you had two O's that you put in.
Yes,
and
yes.
it worked out.
The strategy here is less sophisticated. So we just take all operators up to some length, and then you put all constraints between all of these operators. And so you put all those operators into O as O.
Right.
Some of the constraints take you outside the space of operators that you've considered, and those we just throw away. And all the ones that relate the operators that we're keeping, we use. I mean, it would be fantastic if there was, you know, it doesn't seem impossible, perhaps especially for this one matrix case, which is secretly solvable, you know, but perhaps there is some closed form, maybe there's some closed form thing that's possible, you know. I think there's, actually last time I gave this talk, there was some mathematically sophisticated people in the audience. I mean, I think there is a lot of math of these positivity constraints that I'm not aware of, and it might be possible to do something. Yeah.
Okay. Thank you.
Sure.
Sumit has raised his hand.
Please, I have a question, if possible.
Sorry, one moment. I think there's a raised hand. Sumit has raised his hand, so maybe we can go to Haddad's question next. Sumit, if you can unmute yourself.
Yes.
Question about the two matrix problem. You know, some people have tried to go to some kind of radial polar coordinates in matrix space, like, you know, like take x square plus y square as one matrix and analog of some angle, and, you know, then you diagonalize, you know, that matrix, the x square plus y square instead of x. Do you think these techniques can be used for that?
Let's see. So you're talking about large N, because also for like this model has been studied, you know, for n equals 2 and 3 and so on, and there are these kind of polar coordinates also that I think people.
No, I think this is some large N technology. I mean, I'm not completely familiar with it, but I think people have tried to.
It sounds familiar. I also don't remember if it was for the quantum case or just the matrix integral, because the P's might I don't know.
No, this. Oh.
But maybe.
I have to look at that.
But let's see. I don't know. I mean, this you know, this rotational invariance constraint that we imposed. In principle, should be the same thing, really. I mean,
that would be like.
It may be a more invariant way of, you know, sort of coordinate independent way of restricting things. You could also, maybe another thing you might be saying is that maybe there's a different Born-Oppenheimer ansatz, because this, I mean, you know, you can do whatever you want with this ansatz, right? But it's a bit ugly that it breaks the symmetry. This ansatz is not SO2 symmetric, right? So there might, for example, be a nicer Born-Oppenheimer wave function that you diagonalize radial thing, maybe. So possibly.
Okay. Thanks.
Can I ask a question, please?
Yeah, go ahead, Adad.
Thank you. It's about your plan when you say that you want to characterize the Bfss ground state. What you mean exactly by characterize?
Fair enough. well, at a minimum, it means, let's say, calculate x squared, for example, expectation value of x squared. And the energy, we know, it's 0, okay, because it's supersymmetric. But calculate x squared, calculate the commutator. I mean, so I think things, yeah, I mean, these may not be the most exciting things you'd like to know about the BFSS ground state, but the first things that one could imagine calculating would be something like x squared, trace x squared, 1 over I, something like trace some ij, trace commutator xi, xj, things like this.
Yeah.
Those would be the first things that I would imagine that one might be able to get. Also,
Yes.
maybe supersymmetric analog like this.
I have also another question about the utility of two matrix model. I mean, if we open the door for two matrix model, can we imagine more, maybe 3 matrix model or 4?
Definitely. I tried definitely. So we're going to have to be a little bit more clever. So what we're doing here is quite brute force in a way. But I think that with, yeah, so for example, if you restrict to rotationally invariant operators, for example, you could have strings like xi, xj, pk, but if they're rotationally invariant, you have to contract all the i's, right? So maybe there's like a xi, pj, pk, right? Oh, xk. And so actually, you know, the fact that everything has to get contracted, if you're just going to restrict to rotationally invariant operators, I think might reduce the complexity. Look this way, getting to more matrices it's just a technical question. I mean, just, you know, if we had infinite computational power, we could do it tomorrow.
Are there any physical reason to go more than one matrix model?
Yes, of course. Yeah. So one matrix is far too simple. So all the fun of so the one matrix model doesn't really have sub AD. If you like, if you allow me to abuse vocabulary a little bit, basically, there's not really sub-ADS locality with one matrix. So all the non-trivial questions about emergent locality need more than one matrix. It's definitely crucial. So in ADS-CFT, yeah, I mean, yes.
Yes, I get it. Thank you.
Yeah.
Thank you.
And so I think the conceptual step is going from 1 to 2. Okay, maybe supersymmetry is also important. We haven't, I don't know what the role of supersymmetry is yet, but I mean, I think if we can really crack 2 matrices, I think that's a big step towards, you know, 9 matrices. The step from 1 to 2 is the biggest step, conceptually speaking. And after that, I think it's more a question of computer power.
Maybe we can go to Jyotirmoy next. He has raised his hand.
Hi, sorry. Yeah, so basically, you know, I just wanted to know about a little bit about the numerical techniques that you use. So I presume when you try to find the ground state, I think in your paper you mentioned you use gradient descent, right? So what kind of gradient descent do you use here? Like, you know, is it a simple?
No, I've got to, first let me apologize. So in in the version that is about to get published, we actually added a new appendix with some more details, and I haven't updated it on the archive yet, but I will do that any day now. So there will be some more details very soon on the archive. No, I mean, let's see, it's, I don't think there's anything sophisticated there, right? I mean, there's just a bunch, it's, right, you have let's see, right. You have a bunch of, you have a constrained space. The Hamiltonian only depends on a few of the quantities, right? Because it's just p squared plus x squared plus.
Right. So you pick up those quantities and compute the Hamiltonian, and then you say, you know, among all the available data, which one is the least value? You know, that's what you do.
Yes.
Okay. So, but the technique that you use is just, you know, so when you go down to the least value, you just use a simple gradient descent, or you know, add some velocity, or, you know, I'm just saying that, you know, what optimizes. I mean, have you like?
Yeah. So I should say I have. Shisha has been responsible for technical implementation, but I believe, yeah, and right, yeah.
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 Yeah. Okay. So, can I just again ask one other question on this Born-Oppenheimer thing that you had used for higher number of matrices? Would it? So here, as you say that it kind of boils down to eventually writing dealing with a bunch of harmonic oscillators eventually, right? I mean that's what it comes to. So would it does this have like a nested thing, like when you go up to, let's say if you consider like a 3 matrix, then you can like freeze one and then can you just
yeah, good, thank you. I don't know, there is a subtlety once you actually, yeah, good. I said the big difference between 1 and 2, but that's not quite true actually, for this reason, right? That if I have 3 matrices and I diagonalize one of them, there's still going to be a term in the Hamiltonian which is the commutator of the other 2,
right?
And so it won't actually be Gaussian right away.
Okay.
Now you could still, so that might make it a bit bad, but maybe, I think though you might be able, you might still be able to do that integral actually. Okay, I haven't thought about it. I think, yeah, I must say, I was a little surprised at how well this Born-Oppenheimer wave function does, because it's not controlled. I mean, it's definitely,
it's a guess.
Yeah, I mean, it's not systematic. And if it can do well in other cases too, that would be quite interesting, right? But I haven't. Yeah. So with 3 matrices, yeah. So again, the subtlety might be this commutator term between the 2 matrices that are not diagonalized, but it might be possible to deal with that because. Okay. Yeah. No, I'm not sure.
Okay. Thanks a lot. Thank you.
So can I ask another question?
Sorry, there are other people waiting in line, so maybe
yeah.
You can ask a question after them.
Sorry.
It's okay. So Abhijit, I think, is next in line. So Abhijit, if you can.
Hi, Sean. Hi, Sean. Thank you very much. Yeah, it's a very nice talk. One question. So you briefly made a statement that the solutions that you find are somehow things that saturate these inequalities. Could you elaborate on that?
Yeah, very good. Yes, I was trying to remember exactly how the statement goes. Let's see. So the simplest, yeah, okay, let me pause for 1 second to just try to remember that statement. Right. So yeah, good. Right. So the statement is simplest actually for the matrix integral. Okay. So that's just imagine doing the same thing, but then no p's. Okay. And so you're just doing some integral over matrices. So yeah, right. So the nice thing, right, is that you've got right we write down these operators, right, that are like C1 plus C2x plus, let's even write trace x plus C3 trace x or whatever, x squared, C4x cubed, and so on. Okay. Right. So the main thing is these C's can be negative, right? That's why these constraints are actually quite somewhat powerful. So exactly. And so now let's think about the eigenvalue distribution. So there's rho against x, and that's actually 0 outside some region typically, right? It looks something like some semicircle-like thing. And then so I've gone to the matrix integral case, okay? Just because it's a bit easier.
Mm-hmm. Okay.
And so then what do I want to say? Right, so you want a function, you want functions that are non-zero. So imagine writing down a polynomial, some polynomial p of x, that you try to make it 0 outside, right? Let me get this right. Right, exactly. So trace, exactly, right. So trace of some polynomial of x, right, is the integral of rho of x, the eigenvalue distribution against this polynomial. Okay, so this is not visible at all. Let me start again. Right, exactly. So consider some polynomial p of x, okay? So trace of that polynomial, expectation value, is just the integral over the eigenvalue distribution of that polynomial, okay? And so if, so there should exist such polynomial, basically if you can get a polynomial, yeah, right. So then what you want, okay, I'm getting there. Sorry to go backwards, right? The eigenvalue distribution is only non-zero in some range. So if you can build a polynomial that's almost zero, where the eigenvalue distribution is non-zero, yeah, very good, perfect. Okay, reset, let's say it clearly. So the eigenvalue distribution is only non-zero over some finite range, okay? Now imagine building a polynomial, a high order polynomial, that's almost zero everywhere where the eigenvalue distribution is non-zero, okay? Then the trace, the expectation value of a trace of px squared is almost zero, because you're integrating a function that's zero over some range against a function that's only non-zero over that range, okay? But these are the sort of constraints you're looking for, right? So this suggests that there do exist polynomials that can be zero, right? So it means that you can actually almost saturate the constraint, right? So you can try to find polynomials whose trace is in fact zero, okay? And these will be zero modes of the constraint, right? I'm saying the polynomial, the operator O, okay? The operator O that minimizes the positivity constraint by being exactly zero is one that is sort of zero wherever the eigenvalue distribution is non-zero. And with a high order polynomial, you can manage that. And so that suggests that at least when there's no momenta involved, so in the quantum problem, that it is reasonable that you might actually saturate the constraints, right? That there exists operators, linear superpositions of operators. Of course, you don't know them, right? But there exist very high order polynomials that can give you zero when you integrate them against the eigenvalue distribution. And those will tend to saturate the constraints.
I see.
Is that making sense? And that means it's converging, right? That there is something that it can converge to, and is these guys. But this is for one matrix. I mean,
sorry, just a technical question. So here the x is this your matrix variable x, right? That's what this P of x stands for. Now rho of x dx, there it's an eigenvalue.
Yes. This x is an operator.
Yeah.
So I'm going to the case of one matrix and also with no momentum. Okay, just to,
okay.
That's what this is. So here, trace of p of x. So trace of p x hat, right? Of the operator x, expectation value is equal to the integral over the eigenvalue distribution of p of the eigenvalue.
Okay.
So this gives some intuition about why the constraints might actually be saturated. You might be able to, that there exists some operator that actually saturates the constraints.
And this program, has it been carried out for multi-matrix models, matrix integrals?
Which program?
I mean, not what you just said, but more generally this.
As I'm aware, there are three papers. Okay? So I don't know if so. Yeah. So Henry Lin did. He did the matrix integrals. He did one matrix and two matrices. Matrix integrals. That's what I just told you about. And actually, there's this older paper by Kuczynski and Anderson that also did matrix integrals. And it's a little bit different. They're doing a Yang-Mills theory, but the methods is some 2D Yang-Mills theory. But I think the methods are basically the same, very similar to what Henry Lin did.
I see. Thank you.
Yes, I think, to my knowledge, nothing has been done for 3 or more matrices.
Does the potential that appears in the matrix integral, does it play a big role, or this could be?
I don't know. And for example, it's interesting, like if it has minima and stuff like that. You know, there might be multiple classical saddles and things like this. I don't know. I don't know how that what that will do.
Thank you.
Okay, maybe I can call on Antonio to please unmute your mic and ask your question.
Thank you. So you have this numerical cutoff L, that's basically your computational power. In the case of the conformal bootstrap, when we do these things at finite L, it might converge or not, but at least it gives a rigor as upper bound. In this, for your 2 matrix models, are you providing a rigor as upper bound, or is some estimate?
Yeah, that's a fair. So if one can be confident that the minimization has converged, then this is a rigorous upper bound. No, sorry, wait, let me get it right. Lower bound, right? Exactly. So that's right. So yeah, perfect. Thank you. Thank you. So here's energy, right? And so for a given L, there will exist a minimum energy that's allowed by some L. Now the ground state is certainly allowed, so the ground state will be here, right? So if you're confident that your minimization, that you found the minimum, then it is a rigorous lower bound on the energy. You know, sometimes it depends a bit on the nature of the optimization problem. Okay, sometimes you can be confident about that, but if you're not confident about that, then you don't know. It's an estimate.
Okay.
But in the best scenario, it's a rigorous lower bound.
And what about for the correlators, for the expectation values? Is it
wonderful? So that comes back to plots like this one. So let's see. No, this is rigorous. Yes, exactly. So if you fix, thank you. Yeah, good. Thank you for asking this question. If you fix the energy, then this is a rigorous. Yes, these are rigorous bounds.
Okay. Okay. Thanks.
Okay, do we have any more questions? Okay, well, if there are no more questions, then let's thank Sean again. And thanks for that wonderful talk. And thanks also for bearing with us as we moved your talk a couple of times.
Yes, no problem. Thank you for coming.
Thanks for your time.
I appreciate the questions. Thank you.
Cool.